Good morning, guys, and welcome back to Dynamics course. In this lecture, we're going to start a new chapter, chapter 15, which is about the impulse and momentum in kinetics of particles. In this chapter, we're going to calculate the linear momentum of a particle, and we're going to also find the linear impulse of the forces exerted on this particle, and we're going to use the principle of linear impulse and momentum in order to apply it for the impact between particles. So let's start. Now, what is the definition of linear momentum and what's the definition of linear impulse? In fact, guys, the linear momentum and the linear impulse, they are both vectors, all right? So they are not scalar, they are vectors, all right? Now, the linear momentum is defined as the mass times v in vector form, while the linear impulse is defined as the integration of f dt, which means it's a vector quantity measuring the effect of a force during its time interval of action. In French, linear momentum is quantité de mouvement, linear impulse is l'impulsion. Okay? Now, let's start by the principle of linear impulse and momentum. As we said, the linear impulse is equal to the integration between t1 and t2 of f dt within an interval of time. So it's the integration of the force with respect to time. What does this mean? If I have the variation of this force in terms of time, I can find this I as the area under this force between T1 and T2. And of course, if this force is constant with respect to time, then this area will be the area of a rectangular shape, and it's going to be equal to F, which is constant, times T2 minus T1. So by definition, I, which is the impulse, is the integration of F dt. Now, why should I use the principle of linear impulse and momentum? In fact, so far, we have discovered a lot of principles to be used. In fact, first of all, we started by the general equation of velocity, acceleration, and position, which is in kinematics. And then we went through kinetics by drawing the free body diagram and applying the second law of Newton, sum of F is equal to ma. And then we explained the principle of work and energy, as well as the potential energy and the conservation of mechanical energy if the forces are all conservative. So why do I need another principle, which is here the principle of linear impulse and momentum? In fact, this principle is related to the force with respect to time, and you're going to see that it will be equal to the linear momentum, which means if I have a problem that is involving the force, the velocity, and the time, it's much easier to solve this problem using the principle of linear impulse and momentum. So if I have a problem including the force, velocity, and time, go and solve it using the principle of linear impulse and momentum. This doesn't mean that I cannot solve it using another theories or another principles. You can, but this is the easiest way to solve a problem if it involves force, velocity, and time. Why? Because in fact, I know from Newton's second law that the sum of forces is equal to ma, and I know that a, which is the acceleration, is equal to dv over dt. Now what I'm going to do is to take this dt before the equal sign. So if I take this dt before the equal sign, and I do the integration between t1 and t2, because of course, this is a differential equation, so if I convert it to an integration or an integral equation, then I'm going to have this equation right here. So sum of the integration of f dt between t1 and t2 will be equal to m integral of dv. Now what is the integral of dv between v1 and v2? It's mv2 minus mv1. And what is mv in vector form? If I go back in the slides, this is called what? This is called the linear momentum, mv. All right? So guys, this means that the linear impulse, which is I, the symbol of linear impulse is I, is equal to the linear momentum at state 2 minus the linear momentum at state 1, which means it's equal to the difference in momentum between state 2 and 1. Alright? This equation relates the particle's final velocity v2 and initial velocity v1 with the forces acting on this particle as a function of time. So if I don't know the forces in terms of time, I cannot do the integration. And this also means that mv1, if I take this mv1 before the equal sign, this means that mv1 plus the sum of integration of fdt is equal to mv2. And this reminds me with the equation of kinetic energy T1 plus the sum of work is equal to T2, alright? So it's very similar to this equation, except guys, that this is what? This is a scalar, while this is a vector equation. So don't forget guys, that the principle of linear impulse and momentum is a vector equation. mv1 in a vector form plus the sum of integration of f in vector form dt is equal to mv2, which means the initial momentum plus the impulse diagram is equal to the final momentum. And this is also in vector form. So as you can see guys in this figure, the impulse diagram is very similar to the free body diagram, except that I am showing here the integration of the force in terms of time. So it includes the time duration of the forces acting on this particle. So if I want to convert this vector equation into a scalar equation or into 3 scalar equations in 3D, I have to start by x, for example, in x direction. Then I can apply this equation in x, y, and z. And mvx1 plus the sum of forces in x direction dt is equal to mvx2. And same goes to the other scalar equations. Alright? So I can do the projection of this equation, this vector equation, the linear impulse and the momentum relation equation into x, y, z or any other components. Which means guys, if I need to solve any problem on the linear impulse and momentum relation, I should first establish x, y, z coordinate system. I should, of course, draw the free body diagram. Why? Because I need the forces, right? So I need to draw the particles free body diagram and establish the direction of the particles, initial and final velocity, as you can see here, because in fact, this is a vector equation. So this velocity's direction and this velocity direction will affect my equation. So I need to draw the free body diagram and establish the direction of the particles, initial and final velocities. And I also should draw the impulse and momentum diagrams for the particle. The impulse, it means its integration with respect to time. And then I should resolve the force and velocity vectors into their x, y, and z components. So I'm converting the vector equation into scalar equation, and then I can apply the principle of linear impulse and momentum. And then guys, don't forget the forces must be integrated with respect to time to obtain the impulses. Now, what if I have a system of particles? How can I apply the relation of linear impulse and momentum? Of course, I can apply it. And I can also apply it only for the external forces. Why? Because in fact, if I have a system of particles, the internal forces between these particles will always occur in pairs with equal magnitude and opposite directions, which means the internal impulses will sum to 0 because these forces will be opposite, and then I have the same dt, the same interval of time, then the internal impulses will sum to 0. And this means that I can apply the linear impulse and momentum equation for this system of particles including only the impulse of external forces and not the internal forces. Remember, I always call the external forces big F and the internal forces small f, alright? So as you can see here, this relation between impulse and momentum could be also applied to the system of particles, including only the external forces exerted on the system of particles. Now, as I know, if I have a system of particles, I can find the position of the center of mass by doing this equation. The center of mass position will be equal to the sum of mi Ri over the total mass. And as I know, if I do the first derivative with respect to time, I can find the velocity of the center of mass. And then if I do the second derivative with respect to time, I can also find the acceleration. But here, I am only concerned by the velocity, because in fact the linear impulse and momentum include only the relation between linear impulse and momentum includes only what? The forces, the velocities, and the time, right? So if I do the first derivative of this center of mass position, I can have the velocity of the center of mass as the sum of mi vi over the total mass, and this is called the fictitious center of mass, all right? Now, what if, guys, the sum of external impulses acting on the system of particles is equal to 0? So I'm going to repeat, guys, this is only applied if the sum of external impulses acting on a system is equal to 0. In this case, this term will vanish. And then, if this term vanishes, guys, I'm going to have a conservation of what? Of linear momentum. So in the case of the sum of external impulses acting on a system of particles is equal to 0, the linear impulse momentum equation will be converted to the conservation of the linear momentum. What does this mean and how can I apply it? For sake of simplicity, I'm going to take only two particles, A and B, and I'm going to apply this equation on these two particles. So if I have a system of particles consisting of only two particles, A and B, all right, and I'm going to apply the conservation of momentum because in this case, the sum of external impulses is equal to 0. I'm going to apply the conservation of momentum at T1 and at T2, which means MA VA plus MB VB. This is the linear momentum of the system because it is only consisting of two particles. At T1 is equal to MB VB plus, MAVA plus MVB at T2. Alright? So this is called the conservation of linear momentum. It's only applicable if the sum of external impulses acting on the system of particles is equal to 0. Now, if I divide by the total mass, so if I divide these two terms or these two general terms by the total mass, mt and mt, I'm going to have the velocity of the center of mass for the system of particles. So Vg1 is equal to Vg2. All right? So guys, I want you to remember this relation. There is a conservation of linear momentum only if the sum of external impulses is equal to 0, because I'm going to use this linear conservation in the case of impact. Thank you.